Module 6E focuses on kinetic energy, the kinetic molecular theory, effusion, diffusion, average kinetic energy, actual kinetic energy, etc. Basically, how fast are these molecules moving and how are they behaving? So the kinetic molecular theory of gases, there's two main questions we want to ask here. First, what's causing pressure? Second, how can we explain the gas laws? So what's causing pressure? We've talked about pressure. Pressure is the collisions of these particles. We see these little particles here hitting the sides of the container. That's what's causing pressure. It's the collisions or force over a specific area. How can we explain the gas laws? Well, we've got Boyle's law, Charles's law, Avogadro's law, and Dalton's law to help us understand the gas laws. There are 5 specific postulates of the kinetic molecular theory. Number 1, gases consist of individual particles, moles or atoms, molecules, etc., tiny little pieces, that are in constant random motion. What I need you to think about is, remember, we can have 3 main phases for a molecule can be in 3 phases: gas phase, solid phase, or liquid phase. Solid phase is when it has the least amount of energy and it's locked into a tight, rigid structure. Liquid is kind of the middle ground where it has enough energy to flow around freely, but it keeps the same volume that it had the whole time. Gases have unlimited volume, unlimited shape, because they have the most energy. They're in constant random motion. The volume of gas particles themselves is extremely small compared to the volume of the container. So gases are mostly empty space. The collisions between the gas particles are elastic, meaning that the total kinetic energy before and after a collision will remain unfazed or remain the same. It can be transferred from one to another, but it will remain, the total kinetic energy remains the same. And the attractions between the gas particles themselves are extremely weak and negligible. So as long as the kinetic energy of the molecules is greater than the energy of attraction, the molecules will remain in the gas phase. Remember, these molecules are colliding around, they're hitting each other, they're bouncing off each other, but there is an attractive force there. There's attractive and repulsive forces holding things together. As long as your kinetic energy of the molecules is greater than that energy of attraction, these molecules will stay in the gas phase. The average kinetic energy of gas particles depends only on temperature and is directly proportional to T. That one throws students off. This is average kinetic energy, not the actual kinetic energy of a specific molecule, but the average kinetic energy only depends on your temperature. So, one second before I go to that slide. We can actually use kinetic molecular theory to explain properties of gases. So we know the pressure of a gas is caused by the collision of gas particles with the walls of the container. So we see these, they're bouncing off each other. Here we see them bouncing off each other, but they're also flying and hitting the container itself. They'll bounce, they'll hit the container. That's what's causing your pressure. So the collision of gas particles with the walls of the container. Boyle's law tells us that at constant temperature, the pressure is inversely proportional to the volume, meaning that if the container itself is smaller, has a smaller volume, the gas particles collide with the walls of the container more frequently. So that's why we can talk about like this pressure versus volume thing. All of this is part of our kinetic molecular theory. If I look at the temperature and molecular velocities, we've got Boltzmann's distribution here based on temperature and mass. So kinetic energy, or E sub k, is equal to 1/2 mv squared. E sub k is your kinetic energy, or joules of a single particle. M is your mass. But this does have to be in the proper units. So this is SI units, which means kilogram. And V is velocity in meters per second. If we have two different particles, or in this case, in this graph, we see four different particles. These particles have different masses. The lighter the particle, the faster it travels. We see we've got CO2, O2, N2, and H2O in order of mass. So CO2, O2, N2, and water. And the molecular velocity for water is faster than the rest because it has a smaller mass. At a given temperature, the most probable speed of a gas increases as I decrease that mass. No surprise, smaller particles just travel faster. If I look at temperature though, same molecule, two different temperatures, the higher the temperature, the faster it's going to travel as well. No surprise there either. It's got more energy, so we expect it to travel fast. So as the temperature increases, the average velocity, the root mean squared velocity, we'll talk about more calculating that in a sec. Velocity in general also increases because the particles have more energy. We also see a broadening of the distribution. As we increase temperature. So, what is this relationship between temperature and the average kinetic energy of a gas? We have this equation here. E sub k equals 3 halves RT. Note there's a line over that E, which means average. Basically what this is doing is it's showing us that the average, which is what that is, average kinetic energy only depends on your temperature. It is completely independent of other variables, such as molar mass, pressure, and volume. So E sub k, with the line over it, is our average kinetic energy. R is our gas constant, 8.314 joules per mole K. And T is temperature in Kelvin. So for an example, what is the average kinetic energy of the molecules of air at 298 K? You do need to know this equation. So if you see average kinetic energy, you're going to use this equation. 3 halves times 8.314 joules per mole K times your temperature, 298 K. 3716 joules per mole, which we can convert to kilojoules, 3.72 kilojoules per mole. I don't care if you convert to kilojoules or not if the question doesn't specify, but we do have 3 sig figs here, so I need to round this to 3 sig figs if I do not convert to kilojoules. I would have to round it to 3,720. The four most common gases in the atmosphere are N2, O2, argon, and CO2. Which gas has the highest average kinetic energy at room temperature? Here's the key to this. This says average kinetic energy. Average kinetic energy is only temperature dependent. Any other variable does not matter. These are all at room temperature, which means they all have the exact same temperature. So, all the same average kinetic energy because they're at the same temperature. Average kinetic energy, which is higher in each set? So which has a higher average kinetic energy in each set here? Again, we are looking at average kinetic energy, so it's just temperature. Two liters of N2 at 1 atmosphere and 298 K, or 1 liter of N2 at 1 atmosphere and 500 K. 500 K wins. 1 liter of N2 at 1 atmosphere and 298 K, or 2 liters of helium at 1 atmosphere and 298 K. Trick question, they're the same. 1 liter of N2 at 1 atmosphere and 500 K, or 2 liters of helium at 2 atmospheres and 298 K. Or sorry, it says 45 atmosphere. I changed it from my notes. 45 atmosphere and 298 K. Doesn't matter if it's more moles, doesn't matter if it's higher atmosphere. The average kinetic energy only depends on your temperature. That doesn't mean the kinetic energy, but the average kinetic energy. The other one we need to talk about is your root mean squared velocity. Now, mass does matter on root mean squared velocity. So, what is it and how do I calculate it? It's not, your root mean squared velocity is like your average speed. It's not identical, but it's very close. The equation, you do need to remember, U RMS is equal to the square root, I'll write the square root in just a sec, 3RT over M. You must use SI units for this. So R, your gas constant, 8.314 joules per mole K. T is your temp in Kelvin. M is your molar mass. And here's where it gets tricky. This must be written in kilogram per mole because kilogram is my SI unit. So let's go ahead and actually calculate some so you can see how this works. If you know the equation, you can calculate these through without a problem. Calculate the root mean squared of O2 at 298 K. I could tell you to do it like this, or I could say root mean squared velocity. You have to recognize what that equation is. So I've got O2. O2 has a molar mass of 32 grams per mole, which is the same as 0.03200 kilogram per mole. Or you could write 3.200 times 10 to the minus 2 kilogram per mole. I don't care how you write it, as long as you make sure to convert it to kilogram. U RMS 3RT over M. Gas constant 8.314 joules per mole K, times your temperature, 298 K, molar mass, 0.03200 kilogram per mole, in square root. Now we'll deal with the units, but first let's cancel the easy units. Kelvin, Kelvin, mole, mole. I'm left with joules over kilograms. Here is, again, where students get confused. So let's look at this separately. We've got a joule over a kilogram. I know, though, that 1 joule is equal to kilogram squared second squared. How do I know that? It's a calculated or defined unit. It is the SI unit. You do have to know this. I personally remember it because I think of E equals mc squared. I know m has to be kilogram. C is the speed of light, so meters per second squared. So that's how I personally remember it. I don't care how you guys remember it as long as you remember it, because you have to break that apart to be able to do this calculation here. So what this means is that this joule on top is actually this. Let me move this instead. What this does is it cancels out my kilograms. This whole thing is under a square root though. So now I've got my kilograms have canceled out. And I've got a meters squared per second squared left under the square root. When I calculate this out, I get a calculated answer of 482. But I've got meters squared second squared, take the square root, that is meters per second. Write out the units separately if you're not sure. Come see me, whatever you need to do, but you need to make sure that you're getting the units correct. Second example, helium at 298 K. Helium is a noble gas, not a diatomic. Molar mass, 4.003 grams per mole. So 0.004003 kilogram per mole, or 4.003 times 10 to the minus third kilogram per mole. I don't care how you guys write it. Three times 8.314 joules per mole K, 298 K, 0.004003 kilogram per mole, kelvins cancel, moles cancel, kilograms cancel, leave me meters squared per second squared. Calculate this out. We get 1360 meters per second. So again, your average kinetic energy is only based on temperature, but your root mean square velocity is not exactly identical, but very close to the speed of the molecule itself. So helium has a speed of 1,300 or 1,360 meters per second, whereas O2 is 482 meters per second. That makes sense. O2 is larger than helium, so it's going to travel slower. So notice that 298K, O2, and helium have the same average kinetic energy, but helium has the higher root mean squared velocity than O2 because it is a smaller molecule. Try to keep straight average kinetic energy versus higher root mean squared velocity. Okay, what about effusion and diffusion? What is this relationship between rate and time? There's 3 important points here. First, lighter gases diffuse faster than heavier gases. What do I mean by diffuse? I mean spread through the air. Diffusion is the process by which gas molecules spread out in response to a concentration gradient. The heavier gases diffuse slower than the lighter ones. So by concentration gradient, what do I mean? I mean, like, if I was to spray perfume exactly where I am standing, then that perfume would eventually slowly start to dissipate out from where I initially sprayed it. It's highly concentrated where I am, and it's going to spread out to less concentrated areas. So the diffusion, the mixing of gases throughout an entire container, or diffusion through space if your entire room is your container. Effusion, the leaking of gas through a small opening. Please pause the video if you need to write down the definition of diffusion, because I need to erase it to write down a more specific definition of effusion. But effusion, the process by which a gas escapes from a container into a vacuum through a small hole. Heavier molecules effuse slower than lighter molecules. So by picture, here's diffusion, here's effusion. So diffusion is going to mix by this concentration gradient. Effusion is about how fast can that gas particle get through that little hole. Lighter gases diffuse faster than heavier gases because they just move faster. Diffusion itself works through root mean squared velocity, and your rate is inversely proportional to time. You guys will talk about rate a lot more in the kinetics chapter when you get to that unit, but for now, just realize that it is inversely proportional. So we have root mean squared velocity, and we have Graham's law of diffusion, Graham's law of effusion. So we see that the rate of A divided by the rate of B is equal to the square root of the molar mass of B over the molar mass of A. So these are the rate or effusion rates here. And I know these don't look like it, but these should be molar mass. Couldn't find the right font. So this is why, like, helium balloons only float for a day. Helium has a low molar mass, so it escapes the balloon faster. It effuses faster. So we see helium effuses 2 times faster than methane gas, because of the molar mass of the molecules. So again, when you buy those, you fill those balloons up with helium, they don't float very long because of effusion. But yet, if we blew them up with just oxygen, or not even oxygen, CO2, or our breath, which is mainly CO2 and water vapor, they stay inflated a lot longer. They just don't float because they're more dense than air. So let's go ahead and work a couple calculations. An unknown gas effuses at a rate that is 0.462 times that of nitrogen gas at the same temperature. Calculate the molar mass of the unknown gas in grams per mole. So unknown gas, and I've got a rate that is 0.462 times that of nitrogen gas, same temperature. I want to know molar mass of the unknown gas. So I've got rate of A, which we will say is nitrogen, and molar mass of A, which is nitrogen. Nitrogen is N2, it is a diatomic, so the molar mass is 28.02 grams per mole. Rate of B, which is my unknown, molar mass of B, which is my unknown. And this is what I'm trying to calculate. It tells me that the rate of my unknown is 0.462 times that of nitrogen, but it doesn't tell me what nitrogen is. So, because it's all relative, I'm going to say, okay, the rate of nitrogen is 1, therefore the rate of the unknown is 0.462. Because it's 0.462 times that of nitrogen, it's all about the ratio of them to one another. So our equation, rate of A over rate of B is equal to the square root of the molar mass of B over the molar mass of A. Go ahead and plug in all of our variables. Rate of A over the rate of B, molar mass of B, what I'm trying to solve for, divided by molar mass of A, when I calculate this, 1 divided by 0.462 gives me 2.16. I'm going to have to square both sides to get rid of the square root. .16 squared is 4.67. This gives me the molar mass of B divided by 28.02. Solve for molar mass of B, which is 4.67. Times 28.02, which 4.67, 28.02 gives me 130.8 or 131, because I do have 3 sig figs here, 131 grams per mole. So my molar mass of my unknown gas is 131 grams per mole. A sample of N2O effuses from a container in 42 seconds. How long would it take the same amount of I2 to effuse from the same container under identical conditions? Well, I know my equation. Rate of A over rate of B is equal to the square root of the molar mass of B over the molar mass of A. I've got N2O, 44 grams per mole, and 42 seconds. I've got I2, iodine, or it does tell me I2 in this question, okay, because it is a diatomic, so it should be I2 if it did just say iodine. 253.8 grams per mole, and an unknown rate. In this one, I'm going to rearrange this equation right away. I'm trying to find the rate of B. This will be equal to the rate of A, 42 seconds, divided by the square root of the molar mass of B, 253.8, divided by the molar mass of A, 44, square root of that. This gives me 17.48 seconds, but I have 2 sig figs, so I'm going to round this to 18 seconds. So it's going to take I2 18 seconds to effuse under identical conditions.